In this video, we solve problem 8.4.009 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to find or evaluate the indefinite integral using the substitution x equals 4 secant of theta. So we have this integral. Now they're telling us how to solve it, but if they weren't telling us how to solve it, we would know to use this substitution because of the form of this integral. We might say to ourselves, do we have a rule for that? We'd say, no, we don't have a rule for that antiderivative. And then we might say, okay, would u substitution work if our basic rules don't work? If u is this inside function, and u is generally a function nested inside another function, if u is x squared minus 16, du is a 2x dx. That's the derivative of x squared. And we don't have a 2x out here. We've got an x cubed out here. So that doesn't work, even though we could probably manipulate it even more and evaluate this with a u substitution if we were sort of clever about it. But we would say, okay, basic rules don't work, u substitution doesn't work. But I've got an x squared minus a squared in the integral that reminds us of that secant or that arcsecant antiderivative. Since it looks kind of like an arcsecant problem, but it isn't an arcsecant problem, and basic rules and u substitution don't work, we're going to let x equal a times secant of theta. So when we see this, we go through that whole thought process and we say, since the integrand involves this x squared minus a squared, then we're going to let x equal a secant of theta. So then we would identify a. If a squared is 16, a is 4, then we'll let x equal a, which is 4, times secant of theta. And then we're going to do all of these things over here. I like to think of this as the first step in a 4-step process. We're going to prepare to substitute. Or in other words, we're going to prepare to write everything up here entirely in terms of theta. So we identified a, we let x equal a secant of theta. Now we need to compute dx, because we're going to need to replace that with something in terms of theta. Well, you bring your 4 down, and the derivative of secant of theta is secant of theta times tangent of theta. Don't forget to multiply by d theta. That dx is the derivative times d theta. And then we want to simplify this square root of x squared minus 16. We want to write that entirely in terms of theta as well. We've got x squared minus 16, and x is actually 4 secant of theta, so we can substitute that in. Anytime you've got a product and you're raising it to a power, you can apply that power to each of those factors. So this is going to be 4 squared, which is 16, times secant squared theta. And then we can factor out a 16. And then this is actually tangent squared theta, because we've got this Pythagorean identity. Remember, 1 plus tangent squared of some angle turns out to be secant squared of that angle. So if I subtract 1 from both sides, I find out that tangent squared of the angle is equal to secant squared, minus 1. So this is actually tangent squared of our angle, which is theta in this case. And in general, you would just take the square root of this and the square root of this. So we would get the square root of 16, which is 4. And then we'd have the absolute value of tangent of theta, or the absolute value, the square root of tangent squared is the absolute value of tangent of theta. But whether or not that's positive tangent of theta or negative tangent of theta really depends on some domain issues with this function up here. So it really depends on the values of x for which we're interested in the answer to this question. Since we don't have any x values, since we're just computing an antiderivative, either one will work. So let's just say that this is 4 times tangent of theta when tangent of theta is positive. And then we'll use that in our substitution. Okay, so that was preparing to substitute. And now we want to take everything in our integral, the x that's being cubed, that square root of x squared minus 16 and the dx, and we want to write it entirely in terms of theta. So this is our second step in our process. We're going to substitute. We're going to write the integral entirely in terms of theta. We're going to simplify. And then we will evaluate the integral. And in this case, it's an antiderivative. So you're just making a substitution, replacing every x with whatever x is in terms of theta. So this is x cubed. X was 4 secant of theta. So you just substitute that in. Now here we're substituting the entire square root. That entire square root simplifies to 4 tangent of theta whenever tangent of theta is positive. And then dx, it's not d theta, it's actually 4 secant of theta, tangent of theta, d theta. I guess I didn't leave myself enough room. So this was our dx, this was our radical expression, and this was our x cubed. So we have literally replaced all of these expressions involving x with expressions involving theta. So now we want to simplify. I've got 4 cubed times an extra 4 and an extra 4, so there are 5 4s there, so that's 4 to the 5th. And then I've got secant cubed theta here and an extra secant, so that's going to be a secant to the 4th. And then we have a tangent of theta times a tangent of theta, so that's tangent squared theta d theta. Now at this point, we have a trigonometric integral, and we can use the trigonometric integral guidelines to decide what to do from here. So if you're in my class, you're able to refer to that guidelines sheet. Let me show you what that guidelines sheet tells us. So this is the trigonometric substitution reference sheet, which we're not needing to use here. But after we've done our trigonometric substitution, we get to this point, or we've started our trigonometric substitution, and here we've got powers of secant and tangent. So that was a trigonometric integral of this form, that second one right there. So I'll go to my guidelines, and look, the first one tells us what to do. If the power of secant is even and positive, let u equal tangent of kx. And the power of secant is 4. That's even and it's positive. So we're going to let u equal tangent of whatever our angle is. In this case, our angle is theta. Or I said make a secant substitution, I'm sorry. So make a tangent substitution. And if you read more on that guidelines sheet, it will tell you what to do from there. But the idea is they're going to let u equal tangent of theta, and that means that du is the derivative of tangent of theta, which is secant squared theta, times d theta. And since the power of secant is even and positive, we're actually able to factor out a secant squared from the secant to the 4th and put that off to the side for our du factor. And then everything else that's left over can be written entirely in terms of u equals tangent of theta. So let's do that. I've got 4 secants multiplying each other here. If I take out 2 of them, I'm left with 2 of them. So I've got secant squared, tangent squared here. And then I have the secant squared of theta, d theta on the outside. That's for my du. And then tangent squared theta. If u is equal to tangent, this is just a u squared. And then secant squared, well, that can be written in terms of tangent using this same trigonometric identity, same Pythagorean identity that we used earlier. Secant squared of an angle is the same as 1 plus tangent squared of the same angle. So this is 1 plus tangent squared theta, and tangent is our u, so this is 1 plus u squared. So now I've got 1 plus u squared times du. Now, some students are tempted to just anti-differentiate this and anti-differentiate that and multiply. Don't do it. You need to distribute first. U squared times 1 is, of course, u squared, and u squared times u squared is u to the 4th. Okay, now we just use the power rule from here to anti-differentiate. Oops, different problem. So we've got 4 to the 5th, and the antiderivative of u squared plus u to the 4th du. Now I want to add 1 to the exponent and divide by the new exponent for both of these. Add 1 to the exponent and divide by the new exponent. Don't forget to add c. And then remember what u is. U was tangent of theta whenever we did this trigonometric integration problem. So we back substitute. Okay, so just as a recap before we go on, we're substituting, simplifying, and evaluating the antiderivative. After substitution, we end up here. It's a trigonometric integral. So if we don't know what to do, if we don't look at this and immediately know what the u substitution should be, then we go to our trigonometric integral guidelines, and our guidelines remind us that if the power of secant is even and positive, one way to approach this is to let u equal tangent of theta. Then compute du. Then you want to save that secant squared theta d theta for du. And then you need to write everything else that's left entirely in terms of u equals tangent of theta. So we're saving a secant squared factor, or a squared secant factor if you prefer. For that form of du on the right-hand side. And then you want to write everything in here in terms of u. And in this case, u was tangent of theta. And then we actually do the u substitution. So we write the integral in terms of u. Oops, in terms of u. And then we distribute. U squared times the quantity u1 plus u squared led us here. And it was pretty straightforward. We anti-differentiate using the power rule. And then we back substitute. Now, if we were in 8.3, we would be done. This is the answer. Of course, we would want to simplify that 4 raised to the 5th power. But we're not in 8.3, we're in 8.4. And remember, tangent of theta was just a substitution that we made up in order to evaluate the original trigonometric integral, or trigonometric substitution integral. And so we were able to say that this is equal to this, and through the substitution we were able to get all the way down here, and this is our answer. But we want to go back to x. Like, this is the answer in terms of theta, but theta was just a variable we made up so that we could solve this problem. So we need to write tangent of theta in terms of x. One way that we can write tangent of theta in terms of x is to draw a triangle involving theta and x using this initial substitution. So that's what we do next. That's our third step. So we're drawing and labeling a triangle using our initial substitution. Now I know we've substituted a lot already, but our initial substitution was x equals 4 times secant of theta. So I would take that 4 times secant of theta and solve it for secant by dividing both sides by 4. So secant of theta is x over 4. And remember what secant is. It's the reciprocal of cosine. So cosine is adjacent over hypotenuse. Secant is hypotenuse over adjacent. So when I draw a right triangle with my angle theta here, the hypotenuse has length x when the side adjacent to theta, that's next to theta, but not across from the 90-degree angle, that adjacent side has to be equal to 4. And then by the Pythagorean theorem, this squared plus this squared has to equal that squared. So it turns out that this side is x squared minus 4 squared, or x squared minus 16. Now, if you want, you can go through the Pythagorean theorem and show that if 4 squared plus b squared equals x squared, b squared must be, well, or b must be this expression over here. Okay, so we've drawn our triangle, and the whole point of drawing this triangle is to be able to write this answer entirely in terms of x, not theta. Now, our answer is actually in terms of tangent of theta, so what I need to do is use this triangle to find tangent of theta. Well, from right triangle trig, we know that tangent is opposite over adjacent. So we've got the opposite side of x squared minus 16 and the adjacent side of 4. We're going to substitute that in for theta, or for tangent of theta here and here. So we have 4 to the 5th times 1/3 times tangent of theta cubed plus 1/5 times tangent of theta to the 5th plus c. And tangent of theta is the square root of x squared minus 16. Or the square root of x squared minus 16 over 4, sorry. So if we distribute this, we have 4 to the 5th over 3, and this is going to end up being x squared minus 16 to the 1/2 and then cubed. So if we're raising something to the 1/2 and then cubing it, that's raising it to the 3/2, and then we've got a 4 cubed in the denominator. So I've got a over b cubed, that's a cubed over b cubed, and then I've done a little bit of algebra to get from here to here. And then don't forget to distribute that 4 to the 5th over here as well. So we'll have 4 to the 5th over 5 times this expression raised to the 5th. So we raise this guy to the 5th. So that's x squared minus 16 to the 1/2 power to the 5th. Multiply those exponents. 1/2 times 5 gives us 5/2. And then we're dividing by 4 to the 5th. And you see that the 4 to the 5ths reduce there. 4 cubed reduces with 3 of these 4s. There are 2 left over. And now I have this. I've got 16 over 3 times x squared minus 16 to the 3/2 plus 1/5 times x squared minus 16 to the 5/2 plus c. And that's our answer. So we drew and labeled the triangle using our initial substitution. And then we found tangent of theta using right triangle trig and the sides of this triangle. And then we just substituted. We replaced every tangent of theta with this expression. And then we did a little bit of algebraic manipulation to get from up here to this simplified answer. Probably should have done this algebraic manipulation stuff before as we were working the problem, but I can do it now. So remember, a square root is a 1/2 power. There's an implied 1 there and an implied 2 there. So this is an x to the 1/2, or a quantity to the 1/2, and it's being cubed. Now we have an exponent property that says that if you have something raised to a power and you raise that to a power, all you do is multiply the exponents. 1/2 times 3 got us that 3/2 right there. Similarly, this is x squared minus 16 to the 1/2 to the 5th. So that would be a 1/2 and a 5. When we multiply the 1/2 and the 5, we get 5/2 there. Now for these 4's that are in the denominator, we just use this fact. If you've got a fraction raised to a power, you can raise the numerator to that power and the denominator to that power, and it's the same thing. That's what we did there. And we also distributed that 4 to the 5th to both terms. That way, the 4 to the 5th would reduce with some of those 4's here or all of those 4's there. And if we want, we could take this and differentiate and simplify. And if we do that and differentiate and simplify, we should get that, because that is the antiderivative. That's what an antiderivative is. So we found tangent of theta in terms of x, and then we substituted and simplified. Oops.